So hello again. Tonight we're going to talk about one of the types of observations you can make with amateur radio astronomy, and that's observing the hydrogen gas emissions from the Milky Way galaxy itself, or galactic, as in Milky Way, hydrogen line, as in the emissions of gaseous hydrogen, and then amateur radio astronomy. So, as the saying goes, truth in advertising up front. How I stumbled onto this topic and what I'm presenting and what experience I have. I do have an interest in amateur radio astronomy, or RA. I do have membership in the Society of Amateur Radio Astronomers, and more on that later. I do own multiple types of antennas for doing radio stuff, not just terrestrial, for watching airplane radars flying around my neighborhood, but GPS satellites, NOAA weather satellites, as well as deep space stuff. I've actually received radio signals from the Mars Reconnaissance Orbiter when I was out at Fox Observatory. We once very quickly, for one sample, got a pulsar, and those things are very difficult to pick up. But yeah, I've done a lot of radio astronomy work for an amateur. I have fixed or tripod mounts for antennas that you just sort of point and leave there as the Earth turns, which we'll talk about that, as well as go-to telescope mounts and software-defined radio receivers. And I've used, Raspberry Pi type single board computers to control them all. And if you go on my Facebook page, there's a video of 4 radio telescopes in my kitchen on 4 different go-to mounts, and I commanded them remotely, and they all swing and point to the same part of the sky at the same time. I was trying to do a radio telescope array that had a very accurate time source. I just couldn't find anybody else that wanted to play in that niche. It was too niche for most people, certainly too niche for the SFAA crowd. So I just thought put that over in the corner. I'll get back to it eventually. I do have experience with the Stellarium Planetarium app and using that both for visual astronomy and radio astronomy, software programs for people that are in radio astronomy, something called SDR Sharp, as well as the driver interfaces. And I've worked on a radio astronomy driver for it called SDR that is usable with the Indy library for astronomy. And then I've written a lot of Python code to do astronomical processing. I have recorded some stellar radio source stuff. This is stuff that's like bright stars, quasars, trying to get pulsars, that kind of stuff. And then I've worked with the U.S. National Astronomy Program on setting up one of their software systems on a Raspberry Pi 4 in my house. And I was successful in doing that. It's now an older version of the software. It runs like molasses, because normally you'd run that software on a supercomputer, but I've just got it running on one quad-core Raspberry Pi, so it runs, if they do something in hours, it takes me months. But thus far, my focus has not been on hydrogen line observing. We'll get into what that means. But I have done work on amateur radio astronomy and time stamping the data and formatting the data and how you get it all interconnected and then post-processing the data. But there are aspects of this where you'll see pictures and data that got recorded and such. It's not from me. It's from other members of the Society of Amateur Radio Astronomers, and I have links to their work. I'm not taking their work from them, but it's their work, and I have links to it at the end. People know about astronomy. The people that do the astronomy are astronomers. I'm an amateur astronomer, so you couldn't pay me to do this, as the saying goes. It started out kind of as a hobby and gotten more serious, that I can interact with the SARA folks and understand what they're saying, kind of thing. But astronomy is divided up into receiving from different aspects of the electromagnetic spectrum, X-ray and gamma stuff. I don't have the instruments for doing that. Those are out in space, but I know they exist and I can look up their data and see their stuff. Then the medium energy stuff, the visual, infrared, and ultraviolet, I know about lots of instruments that we have of that. And when Helen was on Sophia, I was kind of her ground crew. So I had to learn a lot of the same stuff that she learned when she was aboard Sophia. I have done work in very low energy, very low frequency, very, very long wavelength stuff. I have an antenna that's received what they call ELF, extremely long wavelength, extremely low frequency data. And so we're going to focus on radio astronomy and in particular, a specific wavelength of that, and it's in radio. So when you talk about the photons that are in radio, what are these things? Well, the duality of photons is such that, well, in radio signals, they often talk about waves or signals or sinusoidal or sine wave stuff. Well, that's kind of what we're receiving is sine waves in radio. But I thought that they were particles. Well, yeah, they're that too, but we're only going to be looking at them as radio waves, and therefore they have a wavelength and a frequency. Frequency is just like oscillations per second measured in units. Back originally was called cycles per second. Nowadays it's called hertz or Hz. The wavelength is measured depending upon how long the wavelength is. It could be measured in nanometers, microns, millimeters, or meters. And there are gravitational wavelengths that are measured in light years, or how far light travels in a year. So they get bigger and bigger and bigger, but scientific notation accepts all of that stuff, and you don't need to keep changing units. The data that comes from these hydrogen emissions, they're not synchronized with one another. So you can be looking in a particular wavelength and not know that, oh, there's another wavelength that you're not looking at the moment that has an even stronger signal. So if you're looking in the 8 gigahertz range, you might find some spacecraft, but you're not going to find a lot of natural phenomena. But if you come down to 1.24 gigahertz, that's hydrogen line. So different frequencies give you different information from the physics that occur in the universe. And also, since they're a wave, you can think of it as when the wave's coming at you versus when the wave is at an angle and coming at you versus when the wave is like 90 degrees coming at you. And all of these things are randomly aligned. They could be aligned not only at angle, but in timing. All their waves are not aligned with one another, even if they're at the same wavelength. So you have to deal with out of phase, in phase, not aligned. And that comes into play with your antenna when you're trying to get the best possible signal, because all this stuff is random. And sometimes if you get two waves and the waves are, opposite to each other, they're out of phase, they'll cancel each other and you have no signal. Or sometimes they're right on top of one another and now they're additive and you have a stronger signal. Have to think about all those aspects of what you're receiving. So what can you look at in radio astronomy? Well, you can look at weird stuff like radio signals from Earth bouncing off the moon. You can look at planets like Jupiter that put out their own radio emissions. The sun puts out its own radio emissions. No, there aren't people on board these planets and the sun, having radio transmitters. These are natural physics phenomenon that emit in certain wavelengths. But then there are also radio bright stars. If our sun is putting out radio emissions, then bigger, brighter stars like Vega, they're definitely putting out radio emissions. And then you have stars at the end of their life that when they collapse down, they produce their own emissions in particular wavelengths. And you have things like pulsars and magnetars. And you have the Crab Nebula, which is a pulsar. And you have the Vela Nebula, which is a really bright pulsar, so bright that amateur radio astronomers use it as kind of like a guide star. When you want to test out your equipment, you know that Vela is a really bright pulsar. And if you can get the timing and the energy levels correct in your instrument for Vela, it's kind of like a calibration mark. And then, of course, there are other galaxies that put out radio signals like quasars. Our Milky Way, a long time ago, was once a quasar when it was feeding. And when it got done feeding, the black hole at the center got done feeding, it was no longer producing that band of radio emissions. And therefore, we went from not a quasar to not a quasar again. Right now, we're not a quasar, but there are lots of other galaxies out there that are quasars. And if you look in a specific range of frequencies, you can find the cosmic microwave background, or the CMB, from the early universe, when everything was just a fuzz, and the fuzz was producing radio waves. And we can still pick up those radio signals. But what we're specifically looking for in this presentation is if you have hydrogen gas and it's being hit by energetic photons, and it excites the hydrogen gas to produce electron transitions, which then, as they fall back, they spit out a photon of radio energy. That particular radio energy is what we're looking for. But how much of it we can see and what part of the sky we're looking in, it's the equipment. How much we see, what the amplitude is, frequency range, all that kinds of stuff.
Monroe, in the
Yeah.
case of hydrogen, it's a molecular vibration. It's not really a photon transition that goes from one level to another. Is the 21 centimeters is the vibration of the molecule.
Yeah. The hydrogen gas by itself is going to have motion. And that's what she's referring to is normally we would identify that as something like Brownian motion, but out in the vacuum of space, it's the hydrogen molecules interacting with each other and with magnetic fields. So anyway, the picture that you see here is a false colored composite of a lot of captured radio signals that are stitched together. And they're all of a particular narrow frequency range, 1.42 gigahertz, or the 21 centimeter band. Actually, I think 21.106, lots of digits, as well as the frequency is 1.420405752 hertz. And it's only about 8 kilohertz bandwidth. So you don't have to tune really far either way. It's like right there is the line. So if you look at this picture, the black, the dark blue, that's the low amounts of energetic hydrogen emitting this particular frequency. And as you see, it gets brighter. And that brightness is the plane of the Milky Way galaxy. What's the orange stuff? That seems really bright. It is really bright. And then you look over on the left side, you see two little orange dots. So why would those be elsewhere? Why are they so bright?
Those are not on our galaxy.
Well, a couple of them aren't.
Those are the nuvens de Magalhães.
Yes, they're the Magellanic Clouds. That's the ones down towards the bottom. But the two brighter ones over in the lower left, those are actually beyond our galaxy, putting out more H-line emission amplitude than our galaxy is. So that's really bright stuff, just not in our galaxy. And you can see the color mapping down in the lower right there. But I didn't zoom in far enough to show you that. So what do you want to use for an antenna? Do I have to have like a 100-meter diameter antenna to receive the hydrogen emissions? No, you don't. How big an antenna do I need? A couple of feet across. That's the one in the top left. That's called a parabolic dish antenna, but it's not a complete dish. It's kind of like an orange slice. You don't have to receive the entire horizontal and vertical width. You just need a slice of the sky. And then it's got specifications for it. You can see that the FOV, the field of view, is if I just look at the sky and I take a single sample, how wide vertically and horizontally is my sample of the sky? And it's 15 degrees by 10 degrees. You can see the 15 and you can see the 10. I don't need any more than that because I want to take just slices of the sky. The gain, the curvature of the mesh dish is amplifying or collecting the radio emissions. And if you look right towards the top center, you'll see this sort of darker thing. You're looking at the back of the dish and the front of the dish points away. And the secondary where it actually receives the signal is pointing out away from the center of the dish. And that collective reflection oscillation gives you 20 dBi inherent gain from the design of the antenna. We'll talk about what antenna gain is in a moment. But if you remember back to the days of hooking up TV sets via coax cables, there was always like, it's 75 ohm coax. That's the resistance in ohms of a known length of section of the cable. If you have TV cables, not cable TV, but TV RF cables, those were typically 75 ohms. If you had amateur radio antennas, ham radio stuff, it was mostly 50 ohm because you wanted to reduce that resistance to get more signal out of the unit. So you bought bigger, thicker cable that had better insulative properties and better grounding separation. And so These antennas come from the TV world, so you'll find a lot of 75 ohm. The software-defined radios come from the TV world, so it all matches out to 75 ohms. But if you look over at other radio stuff like Wi-Fi or 4G, 5G mobile phone stuff, all of that is 50 ohm. So if you want to match it all up, you want to keep your 75s with your 75s and your 50s with your 50s. But there are all sorts of antennas. You'll notice this sort of rod with sticks sticking through the side of the thing. That thing is called a Yagi-Uda, or just a Yagi antenna. And it has a different set of characteristics for field of view and gain. That particular antenna's purpose is Wi-Fi. So it's very good at centering on a 2.4 gigahertz center frequency, because that's what the original Wi-Fi was at. And then in the lower left, that wedge-shaped antenna, that's called a multi-band Yagi. Inside that white plastic, there are actually two printed circuit boards. One is for the low mobile phone band, and one is for the high mobile phone band, and it gives you 11 dB, and it's 50 ohms connection. So you have different antennas for different purposes. And then the two at the bottom are just other examples. I don't have specs for them. The one in the bottom center is known as an end fire helical antenna. And why it does that corkscrew thing, that's to add up all the various phases. And so you can receive over a wider range of frequencies, but it's very narrowly focused. And then the one in the lower right, that's called a pyramidal feed horn, or a pyramidal horn antenna. And that, on a very, very large scale, is how they found the cosmic microwave background. They were looking for bird poop inside the antenna, and they found out, oh, we got rid of the bird poop and we can still see the signal. So a lot of amateurs will build pyramidal horn antennas out of, if you ever see the fiberglass sheets that they use for making air conditioning ductwork, they're metallized on one side and they're fiberglass on the other side. They'll buy sheets of that and cut it out into this specific pyramidal horn shape as 4 pieces that are wedge shaped. And then they'll use air conditioning metal tape to seal it all up. And then they'll put a little probe inside the horn, and that's their antenna. It's a very cheap to make antenna. It's very focused, but there's literally not much in the way of amplification. It's just concentrating the signal. But it's something that amateurs use. Now, you want to get fancier antennas. Let's talk about signal phase, polarization, and arrays. Hydrogen line emissions are randomly polarized. That means they could be coming at you like this, or like this, or like this, or any angle in between. And they're not synchronized. So the waves may be the same frequency, but they're being emitted at different time points. So it's chaotic RF, a chaotic radio frequency signal. Well, how do you make that chaotic stuff better? Use multiple antennas. So if you have an antenna that's vertically polarized or vertically oriented, then it's going to pick up things that are oriented to that. If you also want to pick up the stuff that's like 90 degrees to that, you need a second antenna or a different kind of antenna, like these helical ones. Here's an example. I brought props. This is one of those wedge-shaped antennas, and we can put that in front of my face. You see the little arrow there? That orange arrow? That tells me the orientation of polarization of this antenna. So if I'm looking for a signal that's oriented this way, I should have this side up. If I'm looking for it that way, I have that side up. If you've ever seen antennas that people use in rural sites, like I've got a house way out in the boondocks that I need a really good antenna for my 4G or 5G, you'll see 2 of those wedge-shaped antennas, and they'll be kind of like in a V shape. And because what they do is they have one antenna for this polarization, one antenna for this polarization, and then they wire the 2 antennas together so they add and get a stronger signal. I've actually got one of those on my house because my 5G shoots through a bunch of trees. And so to get a stronger signal, I've got what they call a MIMO antenna. So for larger installations and for professional stuff like deep space work, but not the largest deep space work, for like tracking satellites or watching rockets as they lift off, because you never know what angle the rocket's going to be tilted. So you don't know what polarization angle its transmissions are going to be at. So you have a bunch of antennas that all move together and they add together their polarizations. So you can either have a really capable antenna that amplifies your signal so that even if the signal's out of phase and you lose some of it, you'll still get a strong enough signal off of what is in phase because it's random. But if you have a bunch of antennas all together, it doesn't matter what the polarization is, you can still receive it stronger. So there's a thing called minimum detectable signal. And this is where, people like myself that go looking for pulsars run into a problem. They're very strong compared to something in space that's not putting out any radio frequency. But they're still, very, very tiny fractions of a watt, nanowatts or picowatts. And that amount of energy just doesn't energize your receiver. So you have to have a certain amount of oomph in the signal before your software-defined radio is actually going to be able to tune that frequency. So you want an antenna that's got the right amount of amplification. You might want to put some additional amplification on it, just so that you can get a strong enough signal for your radio to actually detect and receive it. The hydrogen line is a very narrow bandwidth. You don't need like megahertz or gigahertz or even lots and lots of kilohertz. You don't need a very wide signal. FM radio is going to have a much wider signal in bandwidth than hydrogen line. Hydrogen line has 7.682 kilohertz bandwidth. So if you give it 8 kilohertz, you're fine. Now, if you actually want to measure, and we'll discuss this in a moment, the Doppler shift of the frequency of hydrogen, because it's being emitted by the Milky Way galaxy as it rotates. So when you're receiving frequencies from one edge of the galaxy, they're going to be Doppler shifted away from you. And the other side that's coming towards you is Doppler shifted at a different wavelength towards you. So if you just take an amplitude picture of the Milky Way, you'll get a certain amount of data, a certain kind of data. If you take a frequency image of it instead of an amplitude image of it, you can actually see the going away and coming at you rotation of the Milky Way. Different kind of image. Same data, you're just looking at it differently. So what's the miracle of modern science by which we receive all these radio signals? It's a little thing that plugs into a USB port on your computer, and it has an SMA radio frequency cable antenna connection on the other end. And I got to hold up the camera. Here's one. You can see the USB. Sorry, that's the radio frequency connection. It's just a little screw connector. And then the other end is USB. And it's a USB type. Let me get it in my face there. USB type A. Regular old style USB. And it's like USB 2.0. But how do I get an antenna to connect to that? Wow. You need an adapter. And this is an adapter from N to SMA. And the SMA can screw into the receiver. So you have to have things be compatible. It's not just, you got an impedance match with the ohms. You got to have a physical connector match that matches, whatever type of wiring and antenna you have. The cheapest antennas are those with an N-type connector. The ones that cost you more but are better are the ones with an SMA connector because they're special purpose. So inside this gadget, this software-defined radio, I've got version 3, they've got version 4. They wanted to be fancy with the version 4, so they went with black with a white silk screen on it. Inside here, there is a tuner, an analog to digital converter, and the receiver that converts the received digital data into something you can put over a USB interface. So that's what all this gobbledygook is going from radio frequency data to digital data. That's all this does. And you can get these for about $30. So it's not like a fortune. I have a bag full of them because I had arrays of antenna that every one of them needed one of these things. So if I want to radio observe this stuff, how do I go about doing that? Well, you already know you're going to be looking at a specific frequency, and you're going to be capturing the radio signal amplitude, the brightness of this particular frequency. How do I pick that up? How do I like scan the sky? Well, there's three basic ways you can do it. One is the most expensive way, have multiple radio telescopes, and they're all kind of wired together in software. That's called interferometry. That way you can look at a very high resolution image of the sky. But the sky is big, so you don't need that. It's fun to have it, it's fun to do it, but you don't need that. Or you can have an antenna that you mount on a telescope, a regular astronomy telescope go-to mount. So you can actually point it around at the sky, and you can have it like scan the sky taking samples. So it can move across, basically it can paint the sky in vertical and horizontal pixels. Gather all that data together. That costs way less money, but still costs more money. Or you can do what is known as Earth rotation drift scan. This is where you put the antenna on a tripod, you point it up at the sky, and you just let it sit there. And then as the Earth rotates, the sky is stationary because the Earth is rotating within the Milky Way galaxy. And so now you can just have the Earth be the scanner for you, and all you do is just take samples. That's the cheapest approach. And all this stuff connect up. So the diagram you're seeing there goes from right to left, antenna, and then you have the filter that gets rid of noise, and then you have a low noise amplifier to boost the signal. You have that software-defined radio, that little chewing gum stick thing, and then you have a cable, a USB cable that goes into the computer, and the computer has a power supply, and it's probably wired up to some LAN network as opposed to Wi-Fi. Well, on the cables that are not carrying radio frequency, the ones that are either power or carrying digital data like USB, you want to put things on those called RF ferrite choke cords. Now, what this will do is stop other radio frequencies from getting out to your software-defined radio and causing hash, causing interference, radio frequency interference, or RFI, that will be junking your signal. So if your home network has a lot of cabling in it and it's picking up all kinds of stray radio stuff, your home network LAN, your local area network, could care less about that. But if that stuff leaks through your computer over to your radio receiver, it can put like background noise in your radio signal. Or if the power supply to your laptop is, not the best, and it puts out its own radio noise from your home's AC power network, you don't want that getting out to your radio receiver either. So you put chokes on anything where you want to stop the radio frequency from getting out to your receiver. But how do you stop the radio noise from the outside world getting into your receiver? And you'll see there it says filter plus LNA. Filter is, well, if I know I want to receive the hydrogen line and about 8 kilohertz around it and nothing else, I can get a certain kind of filter that will literally be a notch. And anything above or below that, it just gets blocked. So that's the kind of filter. And then, of course, you want to give the antenna a little boost. So you have an electronic, kind of a mishmash of digital and analog that will boost the signal many times. So that's all the pieces. And as I mentioned earlier, you have to have your antennas matching your receivers, and 75 ohm is typical for amateur radio astronomy. And you don't want to have to use adapters. You want to just buy parts that match, because if you have to have adapters, there's coils and stuff involved, and you have loss and reflection and nasty stuff gets involved. So just, if you've got a 75 ohm antenna and a 75 ohm receiver, they're good. Don't go buy 50 ohm cable. But if you've got to adapt things, here's the kind of stuff you want. You don't want a connector, a cable, and a connector if all you need to do is just change the physical connector. You can actually buy connectors that if you tighten them up tightly, there's literally no wire between them. It's just metal on metal. But there's all kinds of connectors. I showed you the N type. There's the SMA type. I don't know why the Wi-Fi crowd did this, but the Wi-Fi crowd said, we'll use the same mechanical connectors as SMA, but we'll make the male pin be the female and the female pin be the male. And so it's called reverse polarity, or RP-SMA. Lots of Wi-Fi antennas and stuff use RP-SMA, but amateur radio astronomy, like, that won't connect together. So be aware of that. So you may find that there's other amateur radio astronomy groups that, like, look at the sun or look at Jupiter. They're called a radio Jove package or program, and they won't bring the signal through a USB interface. To make the receiver even cheaper, what they'll do is they'll have a very small amount of electronics, and they'll bring in the signal as if it's audio, as if it's, you can hear it, but it's a radio frequency that's converted to audio. And then they'll bring that through the computer's like microphone interface. So you're not receiving it using one of these dongles. You're actually just cabling it straight into like the microphone input of your computer. And then you're relying upon the microphone receiver and digital converter in your computer to give you your digital radio data, but it's coming in as audio. So it has to be remapped. That's how things used to be back when computers had USB ports. No, earlier computers never had USB ports. When you couldn't find a computer that had a USB port, or you could find a computer that had like USB 1.1 and you needed a higher speed USB 2.0, those days are gone. If you have a computer that's even like 5 or 10 years old, they're going to have USB 2.0 on them. No reason to do this approach. And I think the next radio Jove that comes out, they're probably going to use an off-the-shelf SDR. The noise source, radio frequency interference. It comes from everywhere. And there's not only like signals you didn't think you were receiving, like side lobes and harmonics and reflections or ghosts. You remember back in the days of the rabbit ear antenna TVs, and you would receive like channel 4, and then slightly offset from channel 4, you'd receive the ghost of Ralph Rennick, as like you'd see two Ralph Rennicks there, one kind of faded and gray, and the other one's like the strong signal. That's a reflection ghost. And yeah, you can have those in cables and all kinds of stuff. So you want to pay attention to sources of radio frequency interference. And one of them is if you hook up your laptop to your receiver and you get all kinds of noise, it's because the Wi-Fi and the Bluetooth interfaces of your computer aren't that great at getting rid of noise. So it's best just to disable them, turn them off, and use a wired cable if you want to get to your home network. And then, like I said, put chokes on things. So noise reduction is done using a filter. And you can see here in the gray in the upper right, you have the antenna. It comes in as a wide selection of frequencies. And then you have a filter that knocks out everything you don't want. And that comes out narrow, your narrow band. And then you have an amplifier or a low noise amplifier that's what actually connects into your receiver. So you take the wideband signal and all kinds of noise, you narrow it down to just what you want, you amplify it, and then that's what you put into your receiver. How do they get these fancy filters so inexpensive? There's a thing called a SAW filter. Not like a saw, it's a surface acoustic wave. Nanomaterials. So if I take a substrate, a little flat piece of like phenolic, and I cut into that a pattern that is the correct separation and height, when the radio frequency goes through, it can actually interact with those things that I cut into the surface, and it creates a standing wave, and the standing wave will only allow things that are at the peak of that harmonic across. So it creates a very narrow filter for you. So whenever you see, I bought an LNA that had a SAW filter. What is it talking about SAW filter? This is a SAW filter, standing wave, surface acoustic wave. It's taking the unwanted radio frequencies and converting them into piezoelectric material. So it's generating essentially a motion from the frequencies you don't want. Now, these devices don't carry a lot of current, very low amperage, but they get just enough to warm up. Think of it as if you look at the separation of my fingers, if I were to warm up my hand behind it at a nanometer level, my fingers are going to spread apart because the surface is expanding from the heat. If I do that, my acoustic wave filter is no longer doing what I expect it to do. So how do they fix this? They have a temperature compensated SAW filter. What they do is, as if it's an integrated circuit chip, they vapor deposit onto the surface of this pattern silicon. The silicon is not to act like a transistor, like a semiconductor. It's so that when the surface heats up, the fingers don't spread apart anymore because the silicon crystals are holding them in place. So it makes a temperature compensated surface acoustic wave filter. Very fancy stuff, but they make them by the bajillions, and therefore they don't really add a significant price to it. So when I'm receiving a signal, I need to receive a signal above whatever the noise is, because if it's not above the noise, I can't receive it. So there's this thing called signal to noise ratio. If I have noise, my noise floor that's a certain level, and then I have my signal that's above that, the power difference between the signal and the noise floor is the signal to noise ratio. If that's too small a ratio, I'm not going to get a strong enough signal out of it to work with that. So I need to make sure my signal to noise ratio is high enough. A really good one would be 20 decibel. So if you later on in the presentation, you see, I just sort of threw together a hydrogen line receiver and it had an SNR of 5.6. Like, that's not a good enough signal. I'd have to go work on that. But that's the reason why you want to narrow your field of view and you want a higher amplitude antenna, is so that you get your signal you want to receive, the power level of that, well above the noise floor. Because if you get it high enough, you can just sort of clip off the noise floor and you now have just signal. So here's a little device called a SAWbird. This is a combination of a SAW filter for hydrogen line as well as a low noise amplifier, and they're fairly inexpensive. This will give you your 20 dB improvement. Just to let you know they're there, and you can see it as a male SMA and a male SMA on both sides. To me, that always seemed weird. Now I've got to have a cable that's one side's got a male and the other side's got a female on it. So if you ever get stuck for, I've got a cable that's too short, it can't like just get there. If you're going to make a cable longer, don't make your RF cables any longer. Make your USB cable longer, because by then it's already digital data. And if there's noise elsewhere, it's not going to affect the digital data. Your quality of your digital data is not impaired by the cable being a little longer. So, if you need to make a cable instead of 6 feet, 10 feet, make your USB cable 10 feet. Don't make your RF cable, 25 feet, because that's the stock size you can buy. If you want to place your computer a really long distance away, like 100 meters or 320 feet, 28 feet away, then you want to put your receiver and your LNA right at the antenna, get it converted to network data, and then have the network data go the long distance. Because you can actually deliver power over that, called power over Ethernet. So you can power the computer that receives the data, the actual receiver, your LNA. You can power all of that by a remote cable, and everything, your data and your power, all in one cable. But that's a whole nother presentation all by itself. Now, obviously, you have to have an open view of the sky. If you have like trees blowing and stuff like that, that's going to affect the quality of your signal. So you want to make sure you have some amount of open sky. The best, obviously, would be 180 degrees by 360. I've had people say, I got into radio astronomy and I cut down some trees, or at least cut back some bushes. So as I mentioned earlier, interferometry, computer automated scanning, or just drift scanning. And most of the time it's inexpensive, so drift scanning. So here's two windows on the same computer desktop. The one on the left is stellarium. That's not a radio signal. That's an optical signal. It's a polar view from where you're at. looking up into the sky. So you can see what radio signals you're getting by, if you look at the center or the one on the left and you look at the signal on the right, that's the signal you're getting by your antenna pointing directly overhead. And you do this over time. You know, in Solarium, you can advance time and see the sky rotate. You record your data over a long period of time, and now you have a bunch of data points that cover the sky. And remember, you can do radio astronomy in the daytime. You don't have to wait for it to be dark. Just don't point at the sun. So what kind of software do you need to do this stuff? Well, the primary piece of software is something called SDR Sharp, because it's written in the C# programming language on a Windows system. The company that has the rights to that right now is a company called AirSpy. So it's called AirSpy SDR Sharp. It used to be just SDR Sharp when there was a hobbyist creating it. And then you need the USB driver specifically for that dongle. So AirSpy SDR Sharp and a driver for it. That's to get the signal from the world of RF into the world of data on a computer. So you install SDR, you fire it, you install SDR Sharp, you fire it up, you confirm that you're actually on the right frequency, and all you're getting is looks like, you know, this wiggly line at the bottom of the display. No pictures, no pretty pictures, but you just want to make sure you're getting the signal. The next thing you need to do is record the data. You may have to adjust the tilt of your antenna angle and then repeat it over several passes to get all the data. And then once you have all the data, you bring it all in and you post-process it. You take all the data, you average it or normalize it, and then you put it all together into stripes of rows and columns, and those become the pixels of your picture. But that comes in as grayscale because it's just voltage levels, it's just amplitude. Now you're going to map that range of voltage levels to different colors, so now you can make a pretty colorful picture. Well, here's SDR Sharp receiving a signal. That very thin vertical red line in the center, that's the center line, and you can see the frequency there at the top. That's the hydrogen line. The gray area around the red, around the center line, that's way too wide. It only needs to be, 8 kilobits, and I have it like 32. But that was just for demonstration purposes. Now, the actual signal itself, if you look in the bottom, that like speckly blue, you see that one little blue line in the middle? That's actually the hydrogen line signal from the Milky Way galaxy. Very narrow compared to very wide reception. So this receiver actually can receive a lot more, a lot wider bandwidth signal than we actually need. So you'll command SDR Sharp when to start receiving and when to stop receiving. And you can actually listen to the noise of the signal being received on the speakers of your computer. And you see the little diagonal line there through the speaker icon. That's because you remember back when you used to tune an analog TV and you'd tune it off of a channel that wasn't there, and you'd see the white noise on the TV and you'd hear like, that's what you'd be listening to, is the white noise of the universe. Okay, so we're receiving the signal, we're converting it into data. Now we need to record the data. You've probably heard the phrase plug-in. You've got a browser and you want to add some specific capability to it. You go find the guy that wrote it and you get that plug-in and you install it in your browser, and now your browser can do new and amazing things. Well, SDR Sharp supports plugins. You want a plugin that will record your data in a manner that you can use it for radio astronomy purposes. So you get a plugin called IF Average. IF stands for intermediate frequency. We're not going to get into that, but IF Average, it will take sort of all the data that's coming in and do a fast Fourier transform on the data as it's being received to average and normalize the range of the data, so you don't have spikes and valleys. And then it will record, store the data on your disk. And it records two different values. It records the in-phase data and the quadrature data. That's the signal coming in like this and the signal coming in like this. because it's very easy to just record those two pieces. And from that, you can, through mathematics, get out the amplitude and the frequency, because as you rotate, you get frequency, because it's a wave moving over an angle. But this particular plugin, you have to get the right version to match the software version of SDR Sharp. And you need another piece of software called the Microsoft XNA framework. This is a set of computer software libraries. So you install XNA version 4, that's the latest. You install SDR Sharp, you install the USB driver, and then you install the plugin, and now you can record data and save it. That's a lot of stuff, but trust me, I've done installations that are a lot more work than that. So luckily, there's one of the SARA members, Alex Pettit, that's actually got a session on the SARA site where they'll walk you through how you get the data out after it's recorded, and then you can make pictures. What he initially does is, if you throw it in an Excel spreadsheet, you have rows and columns, position in the sky, and then values of amplitude. And now you can make graphs out of it, but it's just a waveform, signal change over time. You need to put that through other pieces of software to actually get two-dimensional plots out of it. But let's just talk about mapping. So the data that comes in, the data you store, is grayscale. There's no color involved. It's just brightness. You take the brightness and you say, well, the lowest brightness stuff, let's make that black, like dark sky. The somewhat low stuff, let's make that dark blue. The somewhat brighter stuff, let's make a range of like oranges to reds. And then the brighter stuff will make white. So that's how you false color map the grayscale received radio data to something that looks pleasing to the human eye. Not that number, that number. It's just swapping numbers of a mapping table. So the data that's coming in, once you actually store it, that's just data points. You can use a lot of different kinds of software applications, if you're into writing such things, to do that. Initially, I'm just going to use Excel. It's just data points. Put them in a table, I can plot things. But there are other more sophisticated tools like MATLAB, or you can use Python programming language and write a little script that will draw a pretty picture out of it. These are good for bringing in data, comma-separated values, and then plotting and remapping it. So you don't need exotic or radio astronomy specific stuff. You can start out pretty simple. And also, Excel is likely to have fewer bugs in it than some radio astronomy specific application that only 4 people are using on the planet. And as I mentioned earlier, if you capture the frequency, because remember we're doing the I and the Q branches, we can not only get the signal amplitude, we can get the signal frequency, so the waveform squeezing back and forth. And as the galaxy rotates, the stuff that's going away from you will be red shifted, and the stuff that's coming at you will be blue shifted. So you can see that in the changes of the frequencies that you're receiving on. So you can actually create a plot map that shows the rotation of the Milky Way. That's like the first advanced. After you get the first picture down, now I'm going to do a Doppler shift image. Now, if you're not into packaging all the parts together and you have $300 to spend, the Society of Amateur Radio Astronomers has a packaged kit called Scope in a Box. It doesn't include the computer, but it does include the antenna, the cabling, the software-defined radio dongle, a little tripod to put the antenna on. It's a parabolic dish antenna. It's a package deal. It'll get you up to speed and running sooner, but you pay money for that. I'm cheap, so I buy the parts and build it myself. Oh, they also have links to the software applications for doing the receiving and converting and storing and such. So should you be buying your own cables or just, building them yourself? Like, well, if you're into cable building, fine, build your own cables. But I would strongly recommend that for both radio frequency and USB, if you're not buying it as a kit, buy off-the-shelf cables that match exactly what you need, because then they're manufactured reliably in high volume and they're tested to make sure they work and they don't leak and they don't have RF interference sources and such. That goes for both your RF cables and your USB cables. Now, when you're connecting things up by a USB, depending upon how old or new your computer is, it may have a different version of a USB interface, but they all are backward compatible. If you're using a newer interface, like the dongle uses USB 2.0, and you've got a USB 1.1 computer, older computer, it'll work. It's just you won't be able to get as many samples per second because the interface runs slower. But on the other hand, if you got a brand new computer and it's got USB 4.0 on it, the dongle will only transfer data as fast as USB 2.0. So, going out and getting a fancy, brand new, high-speed USB computer just for doing radio astronomy with a USB 2.0 dongle is probably not the right expensive money. So if you're looking for how fast is it going to go, USB 2.0 will transfer the data 480 million bits per second before you start subtracting out like administrative overheads and packing and identifying the data and such. So that's just for reference purposes there. But if you're into it, if you're not finding, people at your local restaurant or people you normally hang out with, what are you talking about? You should be on the Big Bang Theory. Like, Helen and I experience this when we go out to like restaurants and we start talking about physics or astronomy or something. We get strange looks from people at other tables because, I'll get enthusiastic and start talking with the not, in-home voice. And then we'll get people looking at us like they were the other night at the Thai restaurant when I started talking about Casimir effects. So if you want to talk with other people that are into radio astronomy as amateurs, the Society of Amateur Radio Astronomy is interesting. SARA was actually founded by a former president from decades ago of the South Florida Amateur Astronomers Association. His name is Jeff. But yes, he was a president of SFAA, and he was one of the founders of SARA. And SARA continues on to this day. But if you want to go ask people questions about amateur radio astronomy, this is a good group. It's only about $20 a year to be a member. You get a quarterly email kind of newsletter thing from them, as well as access to a Google group where you can ask questions. But if you want to meet up with them face to face, like minds, like people talking to each other face to face, they hold 2 face-to-face events each year. There is a East and a West conference, and the East conference is held at Green Bank in West Virginia. The professionals allow us amateurs to hang out with them. Very cool. The West one moves around a bit. When there was a solar eclipse that happened about the same time, they held it at the University of Texas outside of Dallas, Texas. But normally when it's available, they'll hold it at the Very Large Array at VLA in Socorro, New Mexico. When that's not available, the kind of professional amateurs at Owens Valley will take pity on us and allow us to hold it there. I've not been to these, but I've been on Zoom sessions where they're doing it. They have a website. It has things you can buy, like you can buy a scope in a box kit, or you can renew your membership dues through their website. They have this really cool event where we just get out online on a Zoom session and we talk to each other. What have you been doing in the last 30 days? So every month we have a thing called Drake's Lounge. Yes, it's that Drake, like the Drake equation. He started those years ago, and though he's not around to continue them, we still have monthly Drake's Lounge events. It's branched out. There's not only a US version, there's an Australian version and a UK version that have their own dedicated sessions. So every month there's like 3 Drake's Lounge sessions. And then for people that want to watch, like sometimes we'll watch Jay when he's doing observing out at his house, and we'll see his telescope moving, and then he'll show us the computer screen and such. The radio astronomers do the same thing. There's once a month a thing called the Radio Telescope Observing Party. You're not looking at the sky, you're looking at a computer display, watching the antenna grab the photons. And if you want to see some prior Drake's Lounge sessions, including Sometimes I make an appearance and uh, will take the debris off the top of my head and spout it to others. They have a YouTube channel for SARA and Drake's Lounge, so you can watch those. There's a lot of them that are already out there. Once you've conquered hydrogen line observing in 2D, how about 3D? If you can get a strong enough signal and you put a go-to telescope mount on your antenna and you scan the sky and you do it in amplitude and frequency, you now have digital data for different dimensions. And you can plot that data in 3D. So instead of just getting a pretty picture that's a flat image, you can actually see the Milky Way as what they call a volumetric image. So you're looking at it from a perspective, and you can actually see the amplitudes or frequencies as curved peaks. So you can say, I see that spike right there. That must be the Magellanic Clouds. Cool stuff. At the professional level, if you want to do radio astronomy, there's a thing called CASA, your tax dollars at work. It's the National Science Foundation, NSF, and they have an organization called the National Radio Astronomy Observatory out at Socorro, New Mexico. That's the DLA. And they have software developers out there. Remember me last session talking about, hey, it's nice that professionals have software people that write stuff for them. CASA is one of those things. So if you get really into amateur radio astronomy and you want serious back-end processing of your data, you can try and set up a CASA node. Like I said, I've got a Raspberry Pi. I would say get a Raspberry Pi 5 if you're into that. But the software is free. It could take you many hours to learn all about it. But once you have a CASA node set up, that might take you a couple of months to process, terabytes worth of data. But the end result is you get a nice, pretty picture if you're into that. So in summary, we've talked about hydrogen line observing. That's a particular frequency and band that you look at the whole sky, and then you put together all your sample data as an image, and then you can show people a picture. You can either buy prepackaged kits to build it all, or you can buy the parts and then just build it yourself. You have to make sure that everything matches your ohms of your cables for RF, your connectors, your USB connectors, USB protocols. You have to have the installed software on your system for SDR Sharp and the plugin and the drivers, and then you can capture data. You can create observations. And then once you have the data, you run it through a bunch of other software that will convert the raw data from just like waveforms into pictures. And if you want to learn how the professionals do it, you can go learn about CASA. And if you want to hang out with like-minded individuals, join SARA. They'd be happy to have your $20 a year. And once every other month or so, we'll get somebody who's brand new to it, who's a newbie kind of thing. And we'll answer a couple of questions. But if they want to take the session off on a deep newbie tangent, we'll get one of the people that's tolerant, that has more experience in educating people, and have them go mentor with them. And then I've got lots of links, lots and lots of links. So if you want to dive into the rabbit hole, all kinds of antennas. And I mentioned things like signal to noise ratio. What's that all about? And then the actual USB dongle that I use. The chips inside the dongle, the tuner and the receiver. USB connections. And then those chokes, what they're all about. But there's actually an Amazon link there. If you find you're getting a lot of RF noise in your signal and you want to put a choke on, they're really easy. You just sort of snap them on the outside of the cable. They used to get bigger chokes than you do, like one wrap wire around the choke. And yeah, there's some people who still do that. But most people they want to tamp it down. So they'll just snap a choke on there, or one choke at each end, double choke it, throttle it. And then reference to the plugin and the Microsoft XNA framework for downloading that stuff. SARA. And then if you want to know about the National Science Foundation or the US's National Radio Astronomy Observatory or CASA, or that the guy that does the automated 3D imaging, or there's actually a presentation you can go through about using the CASA software for hydrogen line image processing. Okay, I know it wasn't everybody's cup of tea, but remember, I'm going to publish this public. I'm going to put this out as public on the YouTube channel for those people that are interested in it. So, comments, questions?
Yeah, so talking about the line of hydrogen, it is kind of interesting because the line of hydrogen helps a lot of things, including calculate distance of galaxies, calculate uh, how far they are, moving, how old certain things in the universe is. So when we look at, because most of the universe is made of hydrogen, so you can recognize some lines in the hydrogen, including that one that is not really like the excitation of the electrons, it's just the vibration of the molecule. And this can help us to understand the universe, knowing that it is a galaxy or is an area that is stellar formation, or it's like there's so much like knowledge that you can take by little squiggly lines that you see in your computer that go just zigzag, but that squiggly lines can tell you can help you to understand the universe. So it's kind of cool to something that you can get. Squiggly lines can kind of boring when you show to the public, but that data gives rise for us to understand most of our own universe.
In our own technology as humans on this planet, we have standardized radio signals that we use for specific purposes, like WWV Fort Collins, Colorado. We have a carrier wave that we use with radio stations. So it's a known thing that we transmit on a known frequency, and it has a certain known bandwidth. Nature does the same thing. The hydrogen line is nature's standard frequency. And as Helen pointed out, you can use that for a lot of different things. But if it's the whole universe doing it, then it's very easy to pick up that signal with very inexpensive equipment. Not as bright as the radio signals from the sun or Jupiter, because those are very powerful, but certainly powerful enough to get a signal to noise ratio above the cosmic microwave background. Now, SETI, the Search for Extraterrestrial Intelligence, they like to listen to the hydrogen line. Why would they pick that specific wavelength? Because it's quiet. It's not really quiet, it's consistent. It's a known amount of energy. And if somebody wanted to communicate across the universe and they wanted you to know this is a technologically advanced source of communications of the radio transmission, if you transmit at 21.1 centimeters at a very high amplitude, anybody listening for hydrogen line will go, that was added. That's not part of normal hydrogen line amplitude. That's far more powerful. That was added. And then if you start modulating that frequency, you'll know that it's got to be something intelligent, because nature wouldn't do that. So that's why SETI, those radio astronomers, tend to look at hydrogen line. But nowadays they're looking at all different wavelengths, because much like we have different radio stations at different wavelengths, they listen to a bunch of different wavelengths looking for signs of intelligent modulation. They're looking in gravity waves too, but because we cannot modulate gravity waves, we don't have the technology. All we're looking at in gravity waves is physics, normal things happening in the universe, like neutron stars smashing into one another, neutron stars being sucked into black holes merging. We see gravity waves from all of that stuff. And so far, we don't have the technology to go, I'm going to modulate my own gravity waves. I did exchange an email with some gravity wave enthusiasts, and they pointed out that while we have the instruments to see gravity waves, even from the mass of ocean water moving. So think of it as the ocean is a very large substance of matter, and the waves, like tsunamis and big ocean waves and stuff, that amount of mass moving around actually creates gravity waves, and we have orbital satellites that can detect those gravity waves. So I sent an email off to somebody who sent an email off to somebody who was actually one of the principal scientists working on that gravity wave experiment. I said, so big, tall skyscrapers, we put these multi-ton giant blocks of concrete up on the top of them to dampen the wind sway of the building. That's a huge mass moving back and forth. Can your gravity wave detector detect that? The frequency is not appropriate and the signal amplitude is too low, but that's a thought. They'd never thought about that. They'd never thought about the mass dampeners in buildings as being a source of gravity waves, but it is. It's just the amplitude is very low and the frequency is very low, and therefore they don't have any instruments that can pick it up. But it's kind of like, yeah, that would produce gravity waves. We just can't see it. So remember, prior to the start of the presentation, we were talking about the James Webb Space Telescope being able to see dusty, deep red, deep infrared galaxies that we can't see with the James Webb, with the Hubble Space Telescope. Same sort of thing. If you have a gravity wave detector, but it can't detect that low an amplitude or that low a frequency, you just don't see them, but they're there. Same sort of thing. You know, if a tree falls in the woods, but you don't have a microphone, you're not going to hear it unless you're there.
Well, the other thing that's interesting about the trees, and so we want to see through the galaxy, right?
Mm-hmm.
But the galaxy, our own galaxy, has full of dust. So it's impossible for us to use visible light to look through and get like the zone of avoidance. So for us to understand the other lanes of the galaxy, the other arms of our own galaxy, because we cannot look up or look down, the only way for us to look is look at the hydrogen line. So you could see through the dust and you can kind of figure out, the shape of our own galaxy. And then because we developed that technology, observing the 21 centimeters way, and we can see through, kind of dust or dark material, solid material, then they go like, hydrogen, right? Our body is made most of water. Water has hydrogen. What about if we use the magnetic nuclear resonance of the hydrogen to observe our own bodies? So then if you're looking to see the lanes of the galaxy, something that you see in a laboratory, but it took like 20 or 30 years. It came out from big observatories in the laboratories, and now is in every hospital. And
Originally,
the magnetic resonance scan, yes, that you can see if you hurt your brain, if you have a fall, or if you have a tumor, or if you have something. So it's like a technology that goes from one area of pure science. Wait a minute, one engineer will figure out a way to use that new idea, that technology, that science, to put something in your hospital or something in your pocket.
Originally, the instrument was not called an MRI. It was called an NMR, nuclear magnetoresonance.
Why did they change it?
They changed it because people were freaked out getting into an instrument that had the word nuclear in it.
Yeah, it's scary.
So they changed it to magnetic resonance imaging. What actually happens is there's extremely strong superconducting magnets that are zipping around in this thing, and the magnetic pump takes all the water molecules, hydrogen in your body, and they're spinning randomly. They're tilted at different phases randomly. It lines them all up very briefly, and it holds them there for a small fraction of a second in the magnetic field. And when the magnetic field collapses, they all want to go spinning again. And when they do that, they give off a radio wave. And the particular radio wave is the hydrogen line. So you have very strong receivers built all the way around the outside of that tunnel that you're in. So magnets make the hydrogen atoms in your body stand up and pay attention. And then when the magnetic field collapses and it goes back, it loses energy and spits out a photon in the radio wave, and the radio receiver around the outside picks up all those. So it's a process that it keeps going bangity, bangity, bang. That's the pulse, the magnetic.
Yeah, the magnet makes us become
And
a
inside
radio.
that round thing, you don't see it, but it's going around like this. It's actually an electronic phase array radio receiver. So it's picking up from all of the excited hydrogen in your body, the radio emissions. And that's how it does the slices.
That's kind of cool that, one science that's used for
Yeah.
one thing ends up being used for something else.
Yeah. Now, are there other excitations that you can perform on materials in the human body to make them spit out radio waves? Yes, but they're a lot more complex and require more expensive equipment. But, water in your body, hydrogen in your body, magnetic fields, that's easy stuff. Particular radio frequency, that's also easy stuff.
Yeah. And then the other thing is that the tissues that you normally observe in nuclear magnetic resonance are soft tissue organs. So like the brain, the lungs, and then that helps a lot to do diagnosis of, aneurysm or tumors or something like that, because soft material. So it's really good instrument for, organs that have lots of water.
Much like nowadays, we can look at astronomical objects in different wavelengths. We can look at them in gamma and X-ray and UV and visible and infrared and radio, and we can actually merge those observations together, and you can see a single picture of a galaxy in a variety of different wavelengths. They can do the same thing medically. They can take a CT scan, which is an X-ray scan, which looks at bones, hard stuff, and then they can take an MRI scan and they can map the two of them together so you can do a 3D computer generated walkthrough of a person's body, not only seeing the organs and the tissues, the muscles, but you can also see all the bones. You can see the porosity of the bones. You can see if there's any hairline breaks or carcinoma in the bones. You can see all of that stuff courtesy of technology. Okay, any other comments or questions?
I guess.
Nothing. I will stop recording.